Welcome to the review for test number 3, which is scheduled for this coming Thursday at the regular time in class. First slide, which of the following best describes a GCM? Well, first off, you need to know that a GCM is a general circulation model. And the one that best describes it is a complex model that simulates the physical, chemical, and biological processes that drive the climate system. So it doesn't model thousands of years, and it's not a simple model, and it's definitely not just a set of statistical equations. What does model uncertainty refer to? The answer is B. Different models can give slightly different answers, and that's just a nature of the slight differences between models. They'll have different ways of describing physical processes, and so that generates slight differences. So when we were talking about when we had the activity on climate projections, you could see that there's changes in the maximum 5-day precipitation. And this question asks, what does that most directly implies? And while it may or may not actually mean an increase in precipitation, but it definitely means that precipitation is more intense. So if you're looking at the amount of precipitation that happens over just 5 days, if you see an increase in max 5-day precipitation, it means it's getting more intense. The fire triangle. You'll remember that from the wildfire lecture. The fire triangle, what is that representing? The fire triangle has 3 elements. So right off the bat, you can kind of look at each of these and yep, they've got 3 elements, right? It's a triangle. But which one is really influencing fire? And the answer is B, ignition. You have to have some way of starting the fire. You have to have fuels. Those fuels have to be abundant and in a particular dryness. And weather. You have to have fire weather. It has to be low relative humidity, perhaps high winds. So that combination of ignition, fuels, and weather are the 3 elements of the so-called fire triangle. These other elements listed here are related to fires, whether it's what contributes to a fire, like the fine fuels and the coarse fuels, and whether you have continuous forests or ladder fuels where you've got the small trees growing up. But all of those things are important. But the fire triangle itself is B, ignition, fuels, and weather. How are increases in the heaviest precipitation related to temperature? So I think you know this one already. I've said it, I don't know how many times. It relates to my favorite graph that shows that warmer air can hold more moisture. And so the answer is D, because air can hold more moisture when it's warm. More water can be available for precipitation, so precipitation can be more intense. And in fact, that's exactly what we see globally. We see a lot more intense precipitation when we have these instances of warmer air. What is meant by a biological adaptation to climate change? So the choices are changes in the behavior of a species, the genetic traits of a species, the spatial range of a species, or a change in the viability of a species or a population. And the correct answer is, in this case, a change in the species traits. You'll remember from the climate modeling lecture that I showed a plot that showed how model results that included both natural forcings and human anthropogenic carbon emissions or greenhouse gas emissions was the only way that you could match the temperature observations with the model output. So the model output, in order to determine if recent warming is related to human activity, what we did, or what climate modelers did, was they had GCM runs forced with anthropogenic and natural emissions relative to warming in the GCM runs. And then they also ran the GCM runs forced with natural emissions only so that they could develop a causal understanding of the role of CO2 forcings from human. And so that answer is D. Also from the climate modeling lecture, or from the emission scenario lecture,
True or false? Relative to other types of uncertainty, the scenario uncertainty, the uncertainty due to how we understand emission scenarios, is greater later in a climate simulation than at the beginning of a climate simulation. And that answer is true. We have a lot more confidence in the scenario and the way that the scenarios represent real life. And then as we get out, several decades out, a lot of other things could change that we don't account for. So scenario uncertainty significantly increases later in a climate simulation.
Climate models, among other things, are useful for which of the following two things? Showing what will happen on a very specific day in the future? No. Attribution, which is identifying the forcings that cause climate change, that's one of the correct answers. Yes, because that gives you a sense of causality. These are climate models that are based on physics, so you can really use them for attribution and detection. C, showing how climate change will impact your neighborhood. No, that's too spatially specific because climate models tend to be more coarse than that in their gridding. And then the second answer is D, testing hypotheses about specific climate changes, and that's the second correct one. So in this case, attribution and testing hypotheses are two useful things that climate models can do. What kind of marine organisms would be most directly impacted by ocean acidification? I went over that in class today. It's organisms that have shells that are made out of calcium carbonate, such as clams or foraminifera or diatoms. Organisms without shells, like dolphins, or organisms that have shells but they're not made out of calcium carbonate, like lobsters, their shells are made out of something called chitin. Same thing for barnacles. But those are not chemically affected by the acidification directly. So it's organisms with calcium carbonate shells, like clams. That answer is A. Algal blooms, generally associated with nitrogen loading. These other things can affect water quality, absolutely. But algal blooms are associated with nitrogen loading.
Why might a species not disperse from a habitat that it's not climatically suitable to one that is? And there's two answers here. One is the new habitat might be unsuitable in some other way. There might be other predators. There could be other factors, especially other than climate. The other is a lack of connectivity. If you can't get to that more suitable habitat, it won't disperse in that direction.
As you learned in Lab 3, non-consumptive use of water refers to water that's used and then typically treated and then made available for another use. So indoor residential water is typically can be reclaimed, reused, whatever. So it can go through water treatment and put back into the river or stream or into the groundwater or some other form of treatment. But that is non-consumptive as opposed to agriculture like irrigation. That is consumptive water use. The plant uses it and then that water goes out into the atmosphere in the form of water vapor. So when it comes to talking about climate change in a constructive way, for instance, over dinner with family and friends, there are some to-dos and not to-dos. One of the big ones is don't consider yourself the expert and make your family and take your family and friends hostage. They are typically not a willing audience. It is a big, deep topic, and most people will be glad to discuss it. No, not at the dinner table. Most people might not even be glad to discuss it. So you're not going to want to jump right into this as a topic of conversation. It's most helpful to first establish common ground and discuss the topic in a location and in a way that's comfortable for everybody. So in this case, the correct answer is D.
This question is about the differences between migration and dispersal. I covered this in class today, Tuesday. So the answer is migration refers to seasonal movement, whereas dispersal is more of a permanent move. Most fires in the western US are ignited by people. Lightning can ignite a lot of fires in places like the Pacific Northwest and some other mountain regions, but most fires across the entire western US are ignited by people. True or false, scientists are in strong agreement that ocean acidification is a consequence of excess emissions of CO2 into the atmosphere. And the answer is true. I showed a plot that showed how changes in um, atmospheric concentration of CO2 increasing in the atmosphere affects the concentration of dissolved CO2 in the ocean, and then how that directly changes the acidity of the ocean, or I should say, it lowers the pH of the ocean because the ocean is still basic. It has a pH higher than 7. In fact, the pH is 8.1 at this present time. So even though we call it acidification, it is still more basic. Ocean acidification can be recognized by a decrease in pH. What is the name of the biome where Reno is located? Well, I hope you know this one by now. I covered it the other day in class. Reno is in a temperate grassland/cold desert. How do higher temperatures impact water quality? Well, the answer is A. It enhances the growth of algae and bacteria, both of these things. A thermocline, which I covered in class today, Tuesday, separates the warmer surface water from colder deep water. And it's different from the pycnocline, which separates less dense surface water from more dense deep water. So we're talking about thermo, it's heat. So it's separating the warmer surface water from colder deep water. There are places where precipitation becomes more intense, but less frequent. And that answer is true. In climate modeling, a projection is what will happen if a given scenario plays out. Is that true or false? So you have, for this one, you need to know the difference between a projection and a prediction. And you'll remember a prediction is what you anticipate the future to be like based on your current knowledge, And so a projection is what will happen if a scenario plays out. So that answer is true.
Now this is a 4-point question because there's 4 different answers you need to write in, or at least write in the numbers, just the numbers. So there are a number of different types of drought. 4 of them are listed here. And I want you to match the definition with each type of drought. So for instance, meteorological drought has to do with precipitation. That's a measure of the departure of precipitation from normal. Agricultural drought refers to not having enough moisture in the soil to meet the needs of a particular crop. So that's number 1. Hydrological drought refers to surface and subsurface water supplies that are below normal. So that's number 4. And then a snow drought is when typically the temperatures are too warm to snow and it rains instead. So that's number 2. Now we're at the longer answer questions. So only answer 4 of these. There are 6, just pick the 4.
Explain 2 ways in which forest conditions after a severe fire can affect snowmelt. So the first of these is carbon shedding onto the snowpack. So you get black carbon shed from the burned trees landing on the surface of the snowpack. It decreases the snow albedo. And the other way is that because the forest canopy is burned off, you get more solar radiation hitting the snowpack. So ultimately you have more sunlight coming in and a lower snow albedo, and you end up having more snowmelt.
In this question, I want you to describe, not just list, one way that climate change can have a direct impact on biodiversity and one way that climate change can have an indirect impact on biodiversity. So you'll want to go back to those biodiversity lecture notes, that section where it's talking about birds and heat tolerance. So, for instance, one way that climate change can have a direct impact on biodiversity is it can push a species outside of its tolerance level. So it's no longer able to survive in a particular temperature, for instance. So an example of that might be the pika. It's too hot for the pika. They can't live in that hot talus anymore because they can't dissipate the heat. Birds don't have evaporative water loss capacity beyond a certain temperature threshold, so you'll have death of little songbirds in desert regions. There's that example that's in the lectures. An indirect impact on biodiversity, and there are many of them, that's where a species or a population's food source might disappear because of climate change, or a species that one population might depend on for food might disappear or move. And so that would be an indirect effect. And so you'll want to maybe provide an example of an indirect impact on biodiversity where, and I'll leave that up to you. Take a look at the lecture notes on biodiversity. So there you go. This one's a really interesting thought question. And the question is the climate predictable? And remember in one of the climate change lectures, I was talking about projections versus predictions. And weather predictions are based on the current state. So we know what the current state is. We have confidence in the current state of the atmosphere. And then therefore, given our understanding of physics and statistical relationships, we can predict the weather out a number of days or even seasonally. Now, is the climate predictable? And so that one is the interesting part. Can you actually predict climate? Well, you can. In fact, we can use models that are based on physics, biology, chemistry to predict what we understand are the fundamental driving forces and how that's affecting climate. We can say climate is predictable, but in more of an aggregate sense. You'll recall those different types of uncertainties, right? So we've got the internal variability uncertainty, which is relatively large at the beginning and gets relatively small towards the end. We've got the scenario uncertainty, the model scenarios, the emission scenarios, I should say. Those start out relatively small at the beginning of the time period, but over 80 to 100 years, those scenarios might not have a lot of predictive capacity. And the same thing with the model uncertainty. We are looking at a lot of different models. Each model gives slightly different results. So the answer to this one, it could be really interesting. Is climate predictable? Yes. Climate models are generally really good. They tell us what's going on, but not on a daily basis. So it's projecting into the future. They're all doing a really good job, especially with temperature, perhaps less so with precipitation. But I'd like you to give a detailed example and provide a substantive counter argument. So in what ways is climate not predictable, right? You're not able to predict what is happening on a day-to-day basis. So 50 years from now, am I going to be able to say, oh yes, that's going to be the hottest June on record, or June 21st is going to be, super warm, or you're going to have a big snowstorm on January 2nd? No, absolutely not. That's weather. You cannot predict the weather out that far. But climate itself there is quite a bit of predictive skill, but there's also counter arguments to that. So I want you to be thoughtful about this particular question. There's a fair amount of leeway here, but do write your answer carefully, clearly, make your arguments cogent. They have to make sense, but I'm looking for interesting arguments, but that makes sense. Okay, thanks. What are 3 ways that species or individuals in an ecosystem can respond to climate change? And give an example of each. These can be terrestrial or marine ecosystems. You can use, 2 terrestrial and 1 marine example. You can use all 3 terrestrial examples, or 2 marines and 1 terrestrial, whatever. Mix it up. But I want to know, what are 3 ways that species or individuals in an ecosystem can respond to climate change? Well, we know that they can move. We know that they can change. They can adapt. We also know that they can die. So what I'd like you to do is give an example of each of those ways that species or an individual in an ecosystem can respond to climate change. And there are a number of them in both the ocean lecture and in the biodiversity lecture. Describe what is meant by aridification. This is a concept that I discussed in the water and climate change lecture. And aridification is the process of a landscape becoming drier simply because the atmosphere is warmer. And that causes more evapotranspiration, more water loss from soils and plants into the atmosphere simply because you have a warmer atmosphere. Again, my favorite graph, when the air is warmer, it can hold more moisture. And there's this process we call atmospheric demand, which is simply that warmer air will pull more moisture from the soil. It'll evaporate more moisture from the soil. Plants will have to use more moisture, transpiring that moisture in order to stay healthy. But that overall process of aridification causes drying out, and that's really what it means. It's the process of drying out the landscape because the atmosphere is warmer. So how does this relate to climate change? Well, a warmer atmosphere creates this condition that induces water to move from the land surface into the atmosphere. So you're losing water from from the land surface, simply because the atmosphere is warmer. So give a physical example of that, and you're welcome to use the example that's in the water lecture, the one where it's showing that part of the western slope of Colorado in the upper Colorado River Basin, where it's had really significant climate warming. And that's a physical example. But I'd also like you to think about a societal impact of aridification. We talked about this in lab also. What are the challenges for irrigated agriculture? What are the challenges in rural areas? What are these societal impacts of this process of the landscape drying out? So again, it's a discussion question. In this last longer answer question, this is from the climate projections class exercise. So I'm asking you a number of questions here. Using this particular figure, what emission scenario was used? So if you look at the very bottom in the small letters there, it says SSP 5-8.5. So that's the emission scenario that's used. Secondly, I'm asking you, what range of years does the map show? And so the map is showing the long term, 2081 to 2100. So that's the range of years. You don't have to say relative to 1981 to 2010. You're welcome to do that. But the years that it's depicting in the map are 2081 to 2100. In what latitudinal region do you see the largest positive change? And note the variable is snowfall. That's a really important thing to think about. Millimeters per day of change of snowfall. So if you see a brown area, which you see significantly along the mid-latitudes there, that means that you're getting less snow, right? And so the answer there is the mid-latitudes. You see, the largest positive change is in the Arctic. It's green up there, more snow. Again, warmer air holds more moisture, it's still cold up in the Arctic, and you'll get more snow. But in this intermediate area, in the mid-latitudes, that's where you have the decrease, the largest negative change. And that's simply because it's warmer and it's probably raining instead of snowing. So the answer to E is the mid-latitudes. And again, the reason for that is because it's simply warmer. You're probably getting more rain than snow. And that is it for this review session. So I look forward to seeing you on Thursday. Hopefully my COVID test comes back negative and I won't be in quarantine, but I will be wearing a mask either way. So I'll see you soon. Thanks.
Here's an extra credit question for you. I've often referred to this plot as my favorite graph. And so I've discussed this in class a number of times. I'm not going to give you the answers to this because it's your job to get that extra credit. But what you need to do is be able to label the x-axis, label the y-axis, But more importantly, describe why this relationship is important in terms of climate change. What is this graph telling you? All right, well, that's it for this review, and I'll see you on Thursday. Thanks.